Good morning and hearty welcome to all on the day 3 of ICDSE 2014 organized by Department of Computer Science, Cochin University of Science and Technology with the technical sponsorship of IEEE Kerala section. Please switch off your mobile phones or switch them to silent mode. We will begin day 3 with a talk by Dr. Mathew J. Palakkal on the topic Digital Information Accessibility for the Blind and Visually Impaired. Dr. Mathew J. Palakkal is the Professor and Associate Dean of School of Informatics and Computing, Indiana University, Purdue University, Indianapolis, IUPUI, USA. He took his PhD in computer science from Concordia University, Canada. His research interests include biomedical text mining and intelligent information management systems. We welcome you, sir.
Thank you. Glad to be here. I want to thank the conference organizers for putting together a great program, and thanks to Dr. Santosh for inviting me to this conference and also to giving me the opportunity to talk. This particular talk may be not in the mainstream of this conference. It's something different, something unique that I hope that there is a message here that you all should take home. That is about this explosive revolution in the digital world, how people like us who has the vision capability are lucky to be enjoying this, whereas there is a segment of population who are not part of this. So this is not my mainstream research. That's next talk. You'll be hearing me a lot today, so bear with me. But this one is something very special I wanted to share with you what we are working on. So I thought this might be a good opportunity to talk about this. To begin with, we all know, we all agree there is such a huge amount of data that is now currently available over the internet. Is it possible to turn the fan on or something? Kind of hot. So, and this information is connected through all different ways, through the wires and wireless, and all sort of possibilities are there. And the growth of this data is exponential. You know, we are now getting into exabytes, and this is 2011 data, and this could be exploding. And you know, if you look at the 2014 data, it is already so large. And this information is also accessible for all of us in many different ways. If you look into the old technology way back in the previous ages to the latest on this side of the slide, where you can have a watch like device, you can wear it, where information can be conveyed and received. Actually, these devices are even a lot more sophisticated, that it can transmit your personal information back and forth also. Now, having said all this, there is a significant accessibility gap. That's what I mentioned earlier. Those who has the ability for vision, or the vision capability, versus people who are blind, that they cannot see. In this slide, you see the children playing with an iPad and so forth, because their vision is their main sensing, whereas children who cannot see use the old style braille dating back to the 1700s, and that gap is, so if you look at it where they are, and they're still operating that medium versus what is happening to the younger generation or like us. And also, this population doesn't have the opportunity, the rich medium that we all enjoy, that is through visualization, animation, interaction, all those things are not available for this segment of the people. So there is a serious gap between the accessibility of information, and that's what this talk is about. As I said, the brain is still the system used by the blind and the visually impaired, and that is what's happening if you go to a blind school or something. The textbooks are in braille, and that's how they learn. Whereas, at least in the US, the material that's used by students are so rich with even whether it is the science topics or math topic or history, whatever it is, full of animations, videos, and this and that. You can interact with it. So the learning environment is a lot richer. Nothing compared to what we are seeing here in the brain system. The other aspect is this information that we are talking about is available over the web too, right? Everything is accessible for visually enabled people. So the question is the web is for all? And it is definitely not. The web is not for everyone. The accessibility for web-based information is limited for the visually impaired, and therefore this is, now when we talk about this information accessibility, there are two aspects to this. One is education and learning. Okay, how this population is not being able to enjoy what we enjoy. Second is workforce development. What kind of jobs these people get? It's very difficult because they are not having the same level of opportunity or familiarity with the technology, like they learn in braille and so on and so forth. What kind of jobs they get? Seldom any, almost IT-related jobs. The kind of jobs that you all get, highly paid, better life, all those things. So this segment again is not being able to get this kind of a quality of life. That's what the point is. With that, we present a concept, an idea that we call the oral world. Okay. Now, for sighted people, we also use sound cues for understanding events that are happening, right? When that fan was turned on, without looking, I know there's a fan was turned on because I'm so used to, my system has an oral map of many concepts. You all have that, right? So when you hear, for example, a fire burning or a siren, you know there is a fire happening or building burning, those kind of concepts are there. Or a windshield or a glass in a car broken, we can understand there is a break-in happening or an accident happened, any of those things. So there is a mapping between the oral sound and concepts. There's a mapping that is in our brain. So many things without looking or seeing, we can hear and we can conclude something is happening, right? So that is the idea here, how to use information access through the oral world. So in this idea, sounds from various sources can be captured and sequences of sound can be transformed into to explain concepts in a manner which is more effective and fun. So the idea is how can we encapsulate various concepts using sound bites, or that's what we call OD. So, for example, just to give you an idea, soil erosion. You're learning science, and one of the science topic is soil erosion. And how soil erosion happens, and what is the consequence of da. This is a chapter or a part of a chapter in the science book. We can, using this physical phenomenon, and sound sort of associated with that concept description, we can concatenate sound bites, which we call OD, and they can learn from that the concept or the process of soil erosion. I will talk about this in more detail. So this is an example I will be using throughout this presentation, how ODIMs can be used to map a process. Okay. So what are ODIMs? ODIMs are approximately 4 to 8 second sound effects. These are macro or narratives or metaphors. Just to give an example, thunder plus lightning crash plus rain means thunderstorm. Okay, so can we encapsulate these kind of simple sound segments to map a concept? The concept here is the thunderstorm. And similarly, animal sounds and different aspect can be put together in an ODIM, and that will represent farm animals. So the question is, can we use the oral space or ODIMs for information access for the visually impaired? Now, we have been working with the blind school children for the last several years, and we use this concept for in a science class. We have children recruited into this, and on the right side you will see the children who use the ODIM concept to learn in 3 topics: the invention of radio, US Constitution, and slavery. And the control group is here. We found out the children would learn much faster and better by using the ODIM concept. Also, interestingly, the retention, the memory and retention was much better after 5 months by using the sound-based learning versus the text-based or the brain-based learning. Now, the big problem is, how do you map the ODIM generation process? How do you map text material information into ODIMs? So the question here is, there are simple sound like the sound of a thunder or the radio, etc., versus more complicated concepts like soil erosion or photosynthesis and so forth. How do you convert this into ODIM map? So with that, the whole idea about content mapping is turn the light off, we'll wash out the slide. And essentially this uses the natural language processing techniques, and that involves a pipeline that is going from the text material all the way into the ODIM mapping, and this is essentially a pipeline. So the first part of this pipeline is text summarization. So the whole idea here is you have a large chapter about one topic. For example, this is a segment coming from a science book, and you take this text material to reduce this into only the essential part of it, what is important in this. And the LSI is an algorithm that is used to reduce the dimensionality of any kind of data, actually. In this case, we use this for text. And it will give you a reduced set of important concepts or important points from a large text. That's what LSI does. It's a computer science popular area, latent semantic indexing. And it's a mapping process from a large space. It could be a text, in this case we are using, otherwise it could be any data that you can map to reduce the dimensionality. In that reduction process you are removing the noise. That is the idea. So that process goes through a mapping. You begin with a document and term matrix and reduces that into a smaller dimensional space that will have the reduced matrix. So the idea here is, again I said, noise reduction through the dimensionality reduction. Those who are interested in latent semantic indexing, maybe you are familiar. It's a very good tool for any kind of dimensionality reduction problem, just like the principal component analysis, actually. We can look at that. And so this will reduce the large text into important concept using this algorithm. Once you have reduced that, the next step is identifying the actor. The actor is what are the key terms in this text. The key actor in the sense that in this text, if you see Conroe problem produces important terms or concepts in the text, we need to identify. For example, who is doing what to what, that kind of an idea, right? So that's important. So then only we can correctly identify the OD mapping process. For this we use a technique, an algorithm called conditional random fields. Conditional random field, some of you may know about this thing. This is a Markov model where the transition functions add associations between transitions to one label to the other, and the state functions help determine the identity of the state. I will tell you what exactly this will do. So the conditional random field essentially looks for the important concepts within the text part of it. I will give you an example. Okay, so the CRF model in this case, and here we have the text line. This is the input, and what we are looking for are important terms in this text line. This is written vertically, and what we are looking for, which of these terms are actors. These are important terms in the text. Now the model takes this text but as features. Essentially a CRF model, conditional random field, is nothing but a set of features and weights, and it will learn during the learning process this set of features and learn to generate an output, a label. That's what we call. So in this case, the features are nothing but parts of speech. These are words that are, say, verb, nouns, adjectives, and so on and so forth. Those are called parts of speech. And this is parsing, the shallow parsing feature. So in this particular case, we are using two different features to represent every word in the sentence, and this is manually provided by the expert. Okay, which one is an actor and which one is not. O stands for others, they are not relevant. You feed this into the CRF model, and the model will learn from a given input stream which ones are important terms or the actor words in it. So here, for example, this is what we will give it to the model. The output, just like a neural network and so forth, you have the output and you have the input stream. And give you an example what is generated from here. So we will assemble a large number of such data that is labeled, generated for learning, goes to the model, and this is what goes into the model, and this is what the model generates, right? For a given sentence, the features and the output predicted, that what is an actor, what is not relevant. So what it is doing is, for example, things like articles and so on and so forth are ignored, and only the important words are identified. So that way we have identified the actors from a given text. CRF is a good model. Those who want to play with the prediction models, it's a good one. In case it can be used for any kind of prediction purposes. Now finally, the actor identification. These are some examples, a set of various examples, and these are actors identified by the condition random field learning model. These are examples. Now we are getting to this. Remember, we need to generate from a given text a set of ODs. That is this process or the pipeline I am talking about. Now, once you have identified the actor, we need to know how these actors are dependent on each other. For example, in the case of soil erosion, we have to make sure who is doing what to what, right? Is the soil is carried by the water or the water is carried by the soil? So that kind of a dependency we need to know. For that, those who are familiar, those who are in computer science, you might know dependency parsers. For example, Stanford dependency parser is something popular. Compilers use dependency parsers to parse your program code. Something like that we can use here. So that's what we are using here. In order to make sure the temporal flow, I mean who is doing what to what, right? The soil loss, the fertile topsoil, plant growth, these are all associated, not the other way around, right? So the parsing techniques, I'm not going to get into this, start with the root, and from there the connection goes like these numbers resembles or corresponds to the flow or the temporal flow of how events happen in the sentence. So that way we can associate properly which one is dependent on each other in the temporal space or like in this order, right? So we need to maintain that. Then only the OD makes sense. The sound, if it is a volcano explosion, we need to have the sound, the ODs occurring in the right sequence. Otherwise, it won't make sense, right? We can visualize that parsing using a dependent parse tree, dependency parse tree. For example, here the moment of soil from one place to another is called erosion. Now the actors are moment, soil, here and erosion. So these are the main actors here, and we also got the right flow or the dependency over there. So with that, the dependency analysis is done, and we have the groupings: soil loss, soil erosion, bare soil. All those things are grouped together. That shows the correct mapping from the raw sentence into the actors and their order of happening. Finally, we have something called a production chain. Production chain is, for a good example, is the food production chain, because things has to happen in a particular order, and similarly we need to have a production chain to represent the step-by-step process taken to build the concept. So for that purpose, we use a production chain construct for the sentences. So from the dependency parser, each group is arranged in a hierarchical fashion, as you can see here, and the production chain is constructed. Okay, so this view helps to understanding various factors that affect a certain concept. So for example, here the concept is soil erosion, and this production chain here, or the group, the production chain, the soil washes a river or stream that causes or blocks sunlight, and it will slow down the photosynthesis. So this is that production chain or the sequence of events that happens. So we say from here we can now generate the ODEs. So the ODEs are, in this case, this is a challenge. This is still mostly a very difficult problem, because when you have a soil, we need to have a sound associated with the soil. So this is just a label for the ODE. And here we have multiple ODE sound or tags. So soil associated with the earth, and the element, dirt, land, terrain, territory, these are all mean soil. So we need to come up with the right sound to represent that. Okay, that sound is generated by an expert. Now, what we do from a computing perspective is, from a given text document, we map it from the production chain, those terms, and we associate it with one of these ODE tags. So when you connect this together, we get the ODE sequence that represents a concept. So this is, for example, what we have generated from and these ODEs generated by the expert is sitting on the database. So we have the database with ODEs and the sequence of concept terms that we generated that has to be connected together. And that's what we are seeing here. We take one of the Odin, we connect this together. This is the Odin string. This is the string that conveys the process of soil erosion. That's what this is, and you can play. So I don't know if I have this reel. I'll see if that plays or not. Yeah, it doesn't play. I have my laptop. It plays. You need an audio file to do that. So what we are seeing here is, unfortunately, I'm sorry you cannot hear it. What you're seeing here is an entire passage that describes soil erosion has been reduced to 1, 2, 3, 4, 5 small segments of sound bites that tells what is soil erosion. Okay, and we have trained of course, just like Braille, one has to get trained on audio. Okay, so there's a learning process, typically 2 to 3 weeks on a concept or a topic, and they listen to this audio and they also listen to the text. Remember, text to speech tools are available. So from that they can hear what this topic is about. Then they will learn how the text is mapped into audio, and that is what they learn at the end. So they get trained on the audio for a concept for n number of iterations. With that, they learn, you replay this, they retain this much better than going through the Braille system. So we have this sort of implemented. We work with the blind school in Indianapolis, in Indiana, and we have been working with them for several years. And this seems to be very exciting for children. Like I said earlier, one thing is a new technology and new opportunity, different from Braille system. They are part of the technology now, and they find this exciting because the whole way of representing material in a different medium, that is sound. Because again, I apologize, I cannot play some of this. It's on my laptop that plays. Those who want to hear this, I can play that for you. So this whole idea is interesting. Now, what we are suggesting is, can we be together, look into this gap, and be part of this coming up with a solution to bridge this gap. We need to do that somehow. This may not be a solution, the solution. There could be other solutions too. So, if you are looking for big challenges, here is a big challenge. That is how to fill this gap, and how can we carry this segment of population along with this, big changes that's happening in the information world. And if this particular concept, this idea is also we are exploring. There's a company in Indianapolis. They are involved in workforce development for the blind people. They want to try to use this for CRMs, that is customer relationship management. People call for help support, and they want to know if they can use this technique and train blind people, for CRMs. So immediately now you're looking at people with a much better work, a different kind of work that might be much better and more exciting, and more importantly, they are part of this. Okay. So that is, I hope to get an idea of what I'm saying. Again, I have another audio to play for you, but this is time. So to conclude, the audio-based content representation for learning would be a viable alternate to Braille. This work is in a very infancy, so there's a long way to go. Our preliminary studies with the BBI, that is the blind and visually impaired children, showed improved retention and recall. That we have some data. Learning process is carried out using a game-like environment that allows BBI people to be more engaged with emerging technologies. The audio-based approach may reduce the information accessibility gap. That's this whole idea is about. This approach may also help to improve IT workforce development. I mentioned that, but a lot more work is needed. I do want to acknowledge my colleague, Professor Steve Mannheimer. This whole OD idea is his, and he's the one who come up with this oral space. And from the computer science is the NLP part, the natural language processing, because we need to convert text into that point where ODs can be connected with the concepts. So that is what I do. We have a system that has been developed and it works and it's in its current form. And also this project was supported by a Google Research Award that we were very excited about. Google funds cutting edge ideas, risky ideas. Also our National Science Foundation is the premier funding agency in the United States for any science related work and some other foundation grants. So that's what I wanted to talk to you about, and thank you for listening. I'm sorry in the beginning the room was very hot. This heat is one thing I'm not being able to handle now. So
basically, entire summary getting translated to audio.
yeah, so what we do is you have a topic, say solar erosion or a photosynthesis or osmosis or any of those things. We play with the science book. So actually what we did was we took the entire 8th grade science book. We digitized that book and then we went by chapter, and this example is all about solar erosion, but we have volcanic eruption, all those kinds of stuff. And each topic we take the key part of it, that text goes through this process. So the first process is reducing this into summary. So we can only focus on a minimal text. And that minimal text, we look at what are the key important terms. Those are the actors, we call it. Then we find what is the relationship between these actors. So
The entire summary is considered for
yes, exactly. The entire summary is considered. So we have multiple sentences. Depending on the summarized part, we may have one sentence, we may have 5 sentences. Now, there is one challenge, again, those who are in computer science here is a challenge for you that I don't know, I don't have an answer yet, is in this, given a paragraph, given a topic, there are 10 sentences that the summarization found that is important. Now, within these 10 sentences, there may be interconnected semantic relationship that's mentioned in second sentence to the 8th sentence or something. See, that's very difficult. Even the dependency parts cannot capture that. We need something more elegant. Remember, this is all in the language compiler area. We are dealing with in that domain here. So somehow, for human, it's so simple, right? We take it for granted. When you read a text, whether it appeared in the top of the sentence, you read it toward the end, you say, oh, it's mentioned there. I know this is talking about that. Think how the machine can do this. It's difficult, very difficult. So that is a problem we need to solve. We encounter that because something is said in the very beginning and that is referred later. How do we connect that? The Stanford dependency parcel it cannot reach that far in finding that dependency. So it needs some other new technique we need to come up with.
And also you are taking explicit summaries.
Yes.
The sentences are actually belonging to the original text.
Exactly. Yeah.
So in that case, that the resolution is very much needed in the
Yeah. Definitely. Yeah. Oh yeah. Definitely. Any questions?
For the training purpose, we are using Marco and Purdue. So some manual input or
We need to generate the label. Yeah. So just like in neural network and all those, the output is this is a supervised learning. So the output label has to be generated. You can do some initial filtering, like the stop words and all those things. In NLP, there are a lot of techniques you can do. You can minimize those. It's like, I wouldn't say throttle manual, it's a semi-manual, semi-automated.
In that Sierra Fall, what was the window size? How many states you have taken for prediction?
In this case, I don't remember, it's been a while. The window size for that is, we need to normalize the size, right? Because the state transition goes from, I need to do that one, I'm not sure. Any other questions? Yeah.
Apart from CRM, CRM is one of the applications. There are other areas where regional challenge can work in the IT.
It's a good question. So, honestly, I don't know. I mean, we are trying to bring this segment of population into workforce, and our particular interest is we are all part of the IT world. We are trying to see whether we can provide workforce in the IT areas. Okay, CRM is an obvious one because they approached us, and so we found out that. Where else can we provide this kind of opportunity for them? I don't know. I mean, in your field might have suggestions. In good welcome, because we are also exploring.
So other question is around the dictionary. So we had like word and the sound. We got like to teach to kind of train that this is the word associated to this is the sound. So something has to become like mainstream. The way we teach young ones is like noun and the picture, so cat and the picture and so on and so forth. Do you envision certain type of app or something like that if you learn them learn in the early ages or the dictionary?
Yeah, so the way we are, there was a bullet in there, we say, what we have done is we created a game-like environment. It's a matrix kind of thing for training, for learning, and that's where they learn. It's like a puzzle, and the puzzle is, initially this puzzle you can see, and then you can associate the object with the puzzle, with the audio. Then you cover the puzzle and they can guess. It's like a memory game. Okay? And we tried that actually. We did this, we did a tour in Hyderabad, met with 1,200 children, and we played this game to see how fast they can learn. So we have a class like this. These are for children with a visual ability, but 7th, 8th grade children just wanted to test how quick they can learn. So we gave this puzzle for 20 seconds, and then we played back this to see how fast they can learn, and it was amazing. And now remember, obviously this is for children, so they can learn quickly. One thing I forgot to mention is also, this is a little bit different from what you're asking, is the visually impaired people, especially when they are young, they have a very fine acuity for sound. Okay, this is part of plasticity. Like when you lose some sensory part, there's a plasticity happens, the brain take over that region. So they have a very amazing ability for sound. Just to give an example, when we visited the blind school, they use the text-to-speech readers, right? There are these tools. It's available. Microsoft provides that. You can click on it. What you see on the screen, it will read for you. And they listen. They play this 5 times faster than how we listen. That the rate at which they listen, we cannot comprehend. Okay, so they have a unique ability. Somebody they get trained a little bit, but that is how they really they browse web. You know, they go just like in a lab. They sit and they browse through the web. They are totally blind, and they listen to the web pages at a speed. When I'm standing next to them, not a word I can understand because it's fast play, right? If you play a tape fast forward, that's exactly how it sounds like. So the equity for the sound and then associating that with the location and all that, they have a unique capability for that. So I don't know if I answered your question correctly or not. I went around on a few places. So we take advantage of this sound perception that drove this idea as a matter of fact. So the training takes time, and we are also looking into different ways of presenting this to them, just like you're saying to the children, how do we do this? And one method we came up with is a puzzle.
So is there an opportunity to use movies? Because movies generally have sound as well as text and some context to gather multiple audience, very machine learning manner.
Yeah, what is the connection? I didn't hear that.
Generally movies have the subtitles, text, and then generally there is sound associated either at the same moment with the text or nearby.
Right.
So is there any opportunity to use movies to gather multiple different audience and make it more automatic rather than the manual part which you talk that experts generate the audience?
That's a good idea. Something to think about. That is possible. Yes, we didn't think along that line. Great suggestion. Yes.
I've tried applying this to mathematics.
Ah,
I've tried applying these techniques proposing mathematics.
I didn't hear the last part. The fan noise is loud.
Mathematics.
What about, in the topic of mathematics? Okay. Well, see, mathematics is interesting, and how do you represent equations? How do you, so we haven't ventured into that yet. It's not just math, physics. And so, like I said, if you look at this as a possibility, we are at 1% progress on this one. Biology is possible, but if you look at physics and hard sciences, it becomes a bit more difficult. And mathematics is very, if you, again, if you visit the blind school, the way they learn math is so painful using the braille system. It is unbelievable. So, to be honest, not yet. But always in the back of our mind, what can we do to use something innovative like this to teach math? And also, don't forget images. That's something like this is an open problem. That's what I was saying. This is, I'm not presenting a research product here. I'm simply presenting a problem that I challenge you all to think about and look into it. So, books, like I said, visually capable people, children, we have all kinds of other medium to learn and entertain ourselves while learning. That is images, right? And animations and things like that. Images, visual aid, images carries a lot of information. How can we encapsulate information like that into a domain like this? Now, keeping in mind, all world is their world. So how can we enrich that? So what we have done is just a baby step in this regarding this. So even with this interesting thing is like history and things like that. It's very volume stuff. So this is very, very useful, and they find it like a history book. So much stuff. They can easily learn using audience, memorize stuff through this technique a lot.
You are, where are you going?